a previous lecture, we were discussing the Newton's method, one of the fastest known optimization method. We have seen that there are quite a few drawbacks of the Newton's method. Those are broadly on the initial point and on the Hessian matrix. We need to have the initial point in the Newton's method very close to an optimum solution, and also the Hessian inverse across iterations are to be positive definite. And this Hessian inverse, the computation of Hessian inverse and the positive definiteness of the Hessian inverse across the iterations are really crucial drawbacks of the Newton's method. In order to alleviate these two crucial drawbacks, we go with the quasi-Newton methods. In quasi-Newton methods, what we do, that we consider an approximation, a positive definite approximation of the inverse of the Hessian matrix. The topic of discussion in this lecture is exclusively Quasi-Newton methods. Neatly, we will consider three topics to be described in Quasi-Newton methods. At first, we will derive two popular Quasi-Newton methods. Those are DFP and BFGS methods. Then we will look at the global convergence, the descent property and the quadratic termination properties of the DFP and BFGS methods. Finally, we will get to know that these DFP and BFGS methods are faster than the steepest descent method but not faster than the Newton's method. Needly, we will get to know that the DFP and BFGS methods have superlinear local convergence rate. We note that so far in solving unconstrained optimization problems, we have gone through two special methods. Those are steepest descent method and the Newton method. In steepest descent method, we consider the direction of movement to be the steepest descent, that is dk is equal to the direction of the negative gradient of the function. And in the Newton's method, we consider the direction of movement to be negative Hessian inverse times the gradient of the function. And we have seen that the steepest descent method has linear rate of convergence and the Newton's method has quadratic rate of convergence. So Newton's method is faster than the steepest descent method, but Newton's method does not have global convergence property, but steepest descent method has global convergence property. And it is found that Newton's method is one of the most successful algorithms for optimization. If it converges, it has rate of convergence at least 2. However, the convergence of the Newton's method is local, that is, convergence to a solution to a stationary point cannot be guaranteed from any arbitrary initial point x0. Moreover, in Newton's method, we need to compute the inverse of the Hessian at each and every iterative point xk to find the direction of movement dk. The computation of inverse of Hessian needs high computational cost, and nonetheless, if the Hessian at the current iterate is not positive definite, the direction of movement in the Newton's method is not a descent direction. So although Newton's method is fast method, it has the crucial drawbacks that it needs computation of the inverse Hessian. The Hessian or the inverse Hessian needs to be positive definite, and even if these two conditions are satisfied, the Newton method has local convergence. That is, the initial point x0 has to be close enough to a stationary point, then only the Newton's method gets converged to a stationary point. So although Newton's method is a fast method, but it has these three crucial drawbacks. And the steepest descent method, although not a fast method, it does not have these three crucial drawbacks. The method steepest descent is slow due to the fact that in computing the direction of movement, we consider to take into account only the first order derivative information of the function. We do not involve the second order derivative information in the computation of the direction of movement in the steepest descent method. And thus, steepest descent method does not take into account the curvature information or the bending information of the given function, and hence the steepest descent method is having a low rate of convergence. But in the Newton's method, we do involve the second order derivative information of the function, we do involve the Hessian of the function, and hence the direction of movement in the Newton's method follows the direction along which the curve may gets bended, and thus the Newton method has fast rate of convergence because it chooses the direction of movement along a particular direction along which the function gets bended. But the Newton's method has these three drawbacks. In order to alleviate the drawbacks of the Newton's method, what we do is we consider the direction of movement dk as negative of some positive definite matrix bk times the gradient of the function at the point xk. If bk is a positive definite matrix, which possibly is an approximation of this Hessian inverse, then bk involves some sorts of second order derivative information of the function. So what we can expect that along this direction if we move, then we are moving along a direction which is approximately the direction along which function has a bending information. We notice that if we take this bk a positive definite matrix, then this dk is certainly a descent direction of the function f, because you just go for computing the gradient transpose dk, you will find that it is given by negative gradient transpose bk gradient of f at xk, which is a negative quantity, and therefore if bk is positive definite, then this dk is a descent direction of the function f. This direction dk is commonly referred as a deflected gradient, as if the direction of the negative gradient has been deflected a bit by the action of this positive definite matrix bk. Now, once this bk is a positive definite matrix, we have seen that this dk is a descent direction. Then instead of using directly the Newton's method, we devise a method that does not use the computation of inverse Hessian but constructs an approximation bk to the inverse of the Hessian, whose accuracy to the actual inverse gradually improves and results in at least a superlinear convergence of the generated sequence xk by following this direction dk. And in constructing an approximation bk to the inverse of the Hessian at the current iterate xk, we do not actually compute or approximate second order partial derivatives but use the previous approximation bk minus 1 and the current gradient information. That is, neatly in constructing bk, we use the previous information that in the previous iterate we have computed bk minus 1, and you use the gradient information of the function at the current iterate xk. Now using these two informations, you go for computing a matrix bk, and in computing bk we actually do not involve the computation of the second order derivative of the function f. And after finding a suitable approximation bk to the inverse of the Hessian, we compute the direction dk given by negative bk times this gradient of fxk. That is, we are replacing the hxk inverse in the Newton's direction by this approximated matrix bk and get the iterative formula as xk plus 1 is equal to xk plus alpha k times negative bk times gradient fxk, where this bk is a suitable positive definite, and also we take a symmetric matrix that approximates or mimic the inverse of the Hessian of the function. where this alpha k is chosen as usual by the exact line search along the direction dk or by an inexact line search along the direction dk. And once this bk is a positive definite matrix, we notice that the generated sequence xk will certainly have the descent property. This iterative formula is referred as Quasi-Newton method or Quasi-Newton iterative formula because this formula looks very similar to the Newton iterative formula just by replacing this minus bk by minus hxk inverse. So I write here this iteration formula is referred to as Quasi-Newton formula. And by the Quasi-Newton formula, we expect that as the direction of movement involves some sort of second order partial derivative information or its approximation, this method is going to be faster than the steepest descent method, and ideally we may expect that the Quasi-Newton formula will have convergence property similar to the Newton's method. That is, we expect that the Quasi-Newton formula will have fast convergence rate like the Newton's method. Now here question comes, how to construct a suitable BK? We expect that the computation of BK across iterations is a bit convenient, not like the computation of inverse of certain matrix so that it will require huge computational costs and all. So question comes that what condition does this capital BK must satisfy and how to construct this BK? Answers to this question are precisely the agenda of this lecture, that is the derivation and analysis of Quasi-Newton method or Quasi-Newton method. So the question before us is, what condition must the matrix BK satisfy and how to construct the matrix BK? Now, in finding the condition that Bk necessarily should satisfy, we recall the derivation of the Newton's method because Bk has to mimic the inverse Hessian, right? So, we recall here the derivation of the Newton's method. In the derivation of the Newton's method, we started our discussion with a twice continuously differentiable function. That is, we started letting that the objective function f of the unconstrained optimization problem is twice continuously differentiable, maybe on an open set, say D, instead of considering f is twice continuously differentiable in the entire n-dimensional Euclidean space. Then we have considered the Taylor's quadratic approximation of the function f, and the next iterative point in the Newton's method is the minimizer or the minimum point of the Taylor's quadratic approximation of the function f at the point xk. Similarly, in the Quasi-Newton method, we consider a quadratic approximation of the function f at the point say xk plus 1 that gives say fx approximately equal to fxk plus 1 plus the gradient at xk plus 1 transpose x minus xk plus 1 plus half times x minus xk plus 1 transpose the Hessian here if we are going for the Taylor's quadratic approximation. But as we do not want to compute the second order partial derivatives, or we do not want to use the second order partial derivative informations, what we do here, we consider a matrix say gk plus 1, a symmetric positive definite matrix that approximates the Hessian of the function f at the point xk plus 1. And then we consider this right hand side expression as a quadratic approximation of the function f at xk plus 1, and then let us try to find what condition gk plus 1 should satisfy so that this quadratic approximation will mimic the Taylor's quadratic approximation that we have used in deriving the Newton's method. Now, to find the conditions that this gk plus 1 should satisfy, let us go for taking the derivative of this function f. Finding derivative of this function, we get the derivative function, say gx, that is the gradient of the function f at x, is approximately equal to, on the right hand side we will have this vector gk plus 1 plus capital Gk plus 1 times x minus xk plus 1. Here I must mention that the notation Gk plus 1 is a usual notation in the optimization methods. Gk plus 1 represents the gradient of the function f at the point xk plus 1. Similarly, Gk will represent the gradient of f at xk. I also inform you that the usual notations that we shall be using in the derivation of these quasi-Newton methods, that Sk is equal to the iterate xk plus 1 minus xk. We also will use yk to represent gk plus 1 minus gk. Now in this approximate equation, setting x equals to xk, we get that on the left hand side gk, that is approximately equal to gk plus 1 plus capital Gk plus 1 times xk minus xk plus 1. So finally we get that bringing this gk plus 1 on the left hand side and then taking the inverse of gk plus 1, we will get gk plus 1 times the vector yk is equal to gk plus 1 minus gk, our usual notation, and on the right hand side we will have approximately equal to sk, where sk is equal to xk plus 1 minus xk. So this is an approximate equation that must be satisfied by the approximated matrix, this gk plus 1 that we have taken over here. Now if we would have taken the function f, the objective function, a quadratic function, then this gk plus 1 is exactly the Hessian matrix of the objective function. And then we will have here exact equality, and finally we will end up with this approximate equality with exact equality, provided the objective function is a quadratic function with positive definite Hessian. So I write here that this approximate equation is exactly with equality for a quadratic function with positive definite Hessian, say capital G, that is for the function fx is equal to half x transpose gx plus some vector b transpose x plus some constant c. And for such a function f, we will have this approximate equality and exact equality, that is we shall have sk to be given by the Hessian matrix G inverse times yk. Or if you do not want to compute the inverse of the Hessian, this equation is given by yk is equal to G times sk. Now we take this equation as an equation to be satisfied by the Hessian approximation or Hessian inverse approximation. And if we take the Hessian inverse approximation as bk plus 1, then we notice that the bk plus 1, which is an approximation of the Hessian inverse, should satisfy bk plus 1 times yk is equal to sk. So for a general twice continuously differentiable function f, we ask to produce the inverse Hessian approximation bk plus 1 in the quasi-Newton method to satisfy the relation that bk plus 1 times yk is equal to sk, which we write here neatly that for a general twice continuously differentiable function f, we ask the produced inverse Hessian approximation bk plus 1 to satisfy bk plus 1 times yk is equal to sk. This equation is called Quasi-Newton equation or Quasi-Newton condition. So this is a condition that we have found that bk must satisfy. Now pre-multiplying both the sides of this equation by yk transpose, we get that yk transpose sk is equal to yk transpose bk plus 1 times yk. And hence if we take this quantity is positive, then possibly the matrix bk plus 1 is a positive definite matrix. So in addition to this quasi-Newton condition to be satisfied by the matrix bk plus 1, we also considered that yk transpose sk is greater than 0 to possibly ensure that the matrix bk plus 1 is a positive definite matrix. So we take an additional condition that yk transpose sk is greater than 0 so that we can possibly ensure that the matrix bk plus 1, an approximation of the inverse of the Hessian at the point xk plus 1, to be positive definite. As inside this condition we have this bk plus 1 getting involved, and bk plus 1 is possibly taking into account some approximation of the second order derivatives of the function f. We call this condition yk transpose sk the curvature condition, because curvature takes care about the bending information of the function and second order derivative information gives us bending information of the function. So in taking the matrix bk as an approximation of the inverse of the Hessian at the point xk, we must keep in mind that the first condition, the matrix bk, is to satisfy the quasi-Newton equation, that is the equation that I have written over here. And the second condition is that to make this bk positive definite, we may seek the help of the curvature condition that sk transpose yk or yk transpose sk is greater than 0. And also we need to take the condition that the matrix bk is a symmetric matrix, because the Hessian for a twice continuously differential function is always symmetric. So we take here bk to be symmetric matrix. And finally, to make the computation of bk convenient, what we take into account that construct bk with the help of the previously computed bk minus 1, that is the approximation of the Hessian inverse at the point xk minus 1 in the previous iterate. And also you may possibly take the information of the gradient at the current iterate, so that the method becomes computationally efficient. Because if we construct bk with the help of the previous bk minus 1 and the current gradient, then we are using some sort of previous memory to find the matrix capital bk. And you notice that in the Newton's method, at each and every iterate we need to compute the inverse of the Hessian, where in computation of the inverse of the Hessian, we do not use the previous memory, the previous Hessian inverse at the previous iterate xk minus 1. So if we go with constructing bk with the help of bk minus 1, the method may be becoming cost effective or computationally efficient. Next, we will now jump on finding an expression of the matrix bk satisfying all these four conditions. Before that, let me make a few quick notes for the quasi-Newton method with the help of this matrix bk. In the quasi-Newton method, we notice that the direction of movement will be given by negative bk inverse times the current gradient, and the iterative formula is given by this conventional equation. Here I must take that this Bk not only symmetric but also positive definite. In fact, inside of this condition, the positive definiteness of Bk will be assured. We will have such a result after the derivation of the Quasi-Newton method. Now, if we go with this Quasi-Newton method with dk as given by this expression, then we will have a few quick notes. Those are as follows. That the first note, we recall that we have seen that the Newton's method is a steepest descent method under the norm, the matrix norm or an ellipsoidal norm with respect to the Hessian matrix at the current iterate. Please relook the lecture note or the lecture video for the Newton's method, and there you will find that I have mentioned the Newton's method is a steepest descent method under this ellipsoidal norm. Similarly, for quasi-Newton method, we can also show that with respect to the matrix norm or ellipsoidal norm given by the matrix Bk, the quasi-Newton method is a steepest descent method. In fact, the quasi-Newton direction dk is equal to minus bk inverse gk is the solution to the following minimization problem. The minimization problem is similar to the minimization problem for the direction of steepest descent. In the steepest descent direction, we have seen that the steepest descent direction is a solution to the minimization problem, minimization of the directional derivative along the direction d, subject to the direction is of unit direction. Here for quasi-Newton method, this dk is the solution to the following minimization problem, that minimization of gk transpose d subject to norm of d with respect to bk, the ellipsoidal norm. You please recall here the expression of an ellipsoidal norm, and to find a solution to this problem you can employ the inequality that gk transpose d its square is less than equal to gk transpose bk inverse gk times d transpose bkd, and equality occurs for d is equal to dk is equal to the quasi-Newton direction, and therefore this dk, the quasi-Newton direction, is a solution to this minimization problem, which is similar to the minimization problem in finding the steepest descent direction, and hence the quasi-Newton direction is called steepest descent direction with respect to the ellipsoidal norm, this norm bk. And here you notice that at each and every iterate, this bk gets changed, and therefore this metric or this norm gets changed, and hence quasi-Newton methods are called variable metric method. So I write neatly here that quasi-Newton method is steepest descent method under the norm bk, and as this norm bk gets changed across iteration to iteration, quasi-Newton methods are called variable metric method. Now for the next note for the quasi-Newton method, we notice that in constructing the matrix bk, we have taken here a condition to be satisfied, that this curvature condition sk transpose yk has to be greater than 0. You might think that this condition might be restrictive, that for any given function this sk transpose yk greater than 0 may not be satisfied. But this curvature condition is not really very restrictive. In fact, if the step length alpha k is chosen with the help of the weak wolf condition, then this curvature condition is automatically satisfied. As a note, let me show it. Yk transpose Sk greater than 0 is not very restrictive. In fact, if we take the alpha k to be chosen that satisfies the weak wolf condition, then we see that in the weak wolf condition we have the condition that grad f at xk plus alpha k dk transpose times dk is greater than equals to some constant c2 times grad f at xk transpose dk, where c2 is a constant in between 0 and 1, which further implies that this gradient of f at this iterate xk plus alpha k dk is xk plus 1 minus grad f at xk transpose dk is greater than equals to c2 minus 1 times grad fxk transpose dk. As dk is a descent direction, this quantity is a negative quantity and this c2 minus 1 is a negative quantity. So finally this is greater than 0. So what we get here, that this difference of the gradient is your yk, its transpose dk, and this quantity is greater than 0. But why this dk is sk divided by alpha k? This is due to the fact that this sk is given by xk plus 1 minus xk, which is equal to alpha k dk, right? And hence you will have dk given by sk divided by alpha k. And finally you then get the curvature condition is satisfied. Yk transpose sk is greater than 0. And therefore this curvature condition yk transpose sk that we will take into account in the construction of bk is not really a restrictive condition. Now as the next note, again we go back to the conditions to be satisfied by bk. We have taken here the first condition that bk is to satisfy the quasi-Newton equation. If we relook at the quasi-Newton equation, then we see that the quasi-Newton equation is bk times yk minus 1 is equal to sk minus 1. This yk minus 1 and sk minus 1, they are two known vectors, two given vectors, two constant vectors. But this bk has to be identified. Bk is a symmetric matrix. Here this bk is an n by n matrix, a symmetric matrix, and hence it has in total half of n times n plus 1 unknowns. You please look at the matrix of bk, then you will quickly find that you will require half of n times n plus 1 many unknowns. You will have in the first row 1 unknown, in the second row 2 unknowns, in the nth row you will have n unknowns. So in total 1 plus 2 plus till n, that gives us these many unknown quantities, and the rest of the quantities in the upper triangular matrix you will have all the quantities as symmetric. So this equation is an equation of half times n into n plus 1 many unknowns, but it has n many restrictions, right? So this quasi-Newton equation has many solutions. There are many bk's for which this equation is satisfied. Out of these many solutions, bk's for this equation, we choose the solution that is closest to the earlier iterate. That is, bk is closest to bk minus 1. To find a matrix bk that is closest to the earlier matrix bk minus 1, we go for solving a minimization problem. Minimize norm of b minus bk with respect to some matrix norm such that this matrix b is a symmetric matrix, a positive definite matrix, and B has to satisfy the quasi-Newton equation BYK is equal to SK. Here you may have different possible choices of the matrix norm, but if we apply the weighted Frobenius norm with respect to the weight matrix W such that its inverse is equal to the average Hessian 0 to 1 integration of Hessian of f at xk plus alpha dk, then we can show that the minimizer of this problem, that is a matrix B that gives a minimum value, will be given by B is equal to Bk plus 1, that is equal to Bk minus this expression. Here I must write the Frobenius norm here. The Frobenius norm of a matrix with respect to the weight matrix W is given by the square root of the matrix W times A into the square root of the matrix W. Here we are pre-assuming that this matrix W is a positive definite matrix, where the Frobenius norm of a matrix is given by the summation of square of all of its entries. Aij is the ijth entry of the matrix capital A. This is what the definition of the weighted Frobenius norm. With respect to this weighted Frobenius norm, that is, here we take this W where W inverse is this matrix. With respect to this weighted Frobenius norm, we can show that the solution to this minimization problem is this matrix Bk plus 1. And surprisingly, this expression of Bk plus 1 is one of the popularly used quasi-Newton update for Bk. And this update is known as the DFP update or DFP formula for the matrix Bk plus 1. Here you notice that Bk plus 1 can be identified with the help of Bk that was computed in the previous iteration and with the help of this Yk that involves the gradient of the function at the current iterate and at the previous iterate. So in computing Bk plus 1, we can keep Bk in memory and obtain new Bk plus 1 from the last Bk, and this will result in a much cheaper procedure than the original Newton method. In the original Newton method, we have to keep computing Hk inverse afresh at each and every iteration. But this Bk plus 1 is although afresh computed, but the computation of Bk plus 1 is done with the help of Bk and the iterative sequence xk, and this results in a much cheaper procedure. So I write here this update is known as the DFP update or DFP formula for computing Bk plus 1. We will have a detailed derivation of this Bk plus 1 just after a while, but before that let me just make the final note for this quasi-Newton method, that what is the geometry of this quasi-Newton method. For the Newton method, we got to know the geometry of the Newton method, that to find a zero of y is equal to gx, where g is the derivative of the function f, which is a function of one variable say, and to find a zero of this gx, what we do, that at the current iterate xk, we draw the tangent to the curve y is equal to gx, take the point of intersection of this tangent with the x-axis as the next iterate xk plus 1, and this xk plus 1 we all know in the Newton's method is given by xk minus gxk divided by g dash xk. For the quasi-Newton method, there is a similar geometry which is as follows, that for a function of one variable, say f, the quasi-Newton equation gives that some bk plus 1, a real number, times yk, where yk is the gradient here, the derivative at the point xk plus 1 minus the derivative at the point xk is equal to sk, where sk is given by xk plus 1 minus xk. Notice that for a function of one variable, the matrix bk plus 1 reduces to a matrix of 1 by 1 and hence a real number. And this quasi-Newton equation aims to find a solution of f dash x is equal to 0, or aims to find a solution of gx is equal to 0. It aims to find a stationary point of f or a solution to gx is equal to 0, where this gx is the derivative of the function f. Now in terms of g, this equation, this quasi-Newton equation is gxk plus 1 minus gxk divided by xk plus 1 minus xk is equal to bk plus 1, which gives the slope of the chord joining these 2 points xk gxk and xk plus 1 gxk. Thus, the quasi-Newton equation is also referred as the secant equation or the chord equation. And accordingly, the quasi-Newton iterative formula, which is given by xk plus 1 is equal to xk minus bk times gk or g at xk, that gives the 0 of the chord y minus gxk divided by x minus xk is equal to bk inverse. We see from this equation of chord that if we put here x is equal to xk plus 1 and y is equal to 0, we get this identical equation. This xk plus 1 is equal to this expression. That is, this xk plus 1 is a 0, that is the point of intersection of this chord with the x-axis. That is the geometry of the quasi-Newton iterative formula, and accordingly the quasi-Newton iterative formula is also referred as the secant update or secant method for optimization. So we write here that the quasi-Newton method is also referred as secant method. The Newton's method, which is also called Newton-Raphson method, is called the tangent method in optimization. So in this note, the note 4, we have seen that the quasi-Newton method is following a secant update, and here in note 3, we have seen that the quasi-Newton method is a least change method. Least change from the earlier evaluation of the matrix Bk. So accumulately this note 3 and note 4, commonly quasi-Newton method is referred as the least change secant method. Now after all these 4 notes, let us go for deriving this Davidson-Fletcher-Powell method, or abbreviately the DFP method or the DFP update for the matrix Bk plus 1. The DFP method is derived as follows: that in finding bk plus 1, which is an approximation of the Hessian inverse at the point xk plus 1, we add two symmetric matrices, each of which is of rank 1, with the earlier matrix bk, that we consider bk plus 1 is equal to bk plus some constant alpha, real constant, times u transpose plus beta times v transpose, where alpha and beta are two scalars, two constants, and u and v are two vectors taken from Rn. Note that if u is a vector in Rn, then u transpose is a matrix of order n by n but of rank 1. So in finding bk plus 1, we are adding two rank 1 matrices with the earlier matrix bk, and thus this bk plus 1 is called rank 2 modification of bk. So we are considering a rank 2 modification of bk where we are adding this alpha uu transpose and beta vv transpose with the matrix bk. So to find this bk plus 1, we have to determine these four quantities: two real numbers alpha and beta, two constants, and two vectors u and v. Now to determine these possible values of alpha, beta, u and v, we look at the quasi-Newton equation that has to be satisfied by the matrix bk plus 1. From the quasi-Newton equation that is to be satisfied by bk plus 1, we get that bk times yk plus alpha times uu transpose times yk plus beta times vb transpose times yk is equal to sk. Note that this is a system of n equations with how many unknowns? You have n many unknowns, n components in u, you have n more many components in v, you have alpha and beta. So this equation is a system of n equations with n plus 1 plus 1, total 2n plus 2 unknowns. Clearly then u, v, alpha and beta are not uniquely determined. So here we go with choosing some value of u and v that would satisfy this equation. We notice that if we choose u and v by u is equal to say sk and v is equal to bk times yk, we have from this equation that bkyk plus alpha times sk transpose times yk. Here we may apply the associativity property of matrices plus beta times bkyk times yk transpose bk into yk. This is equal to sk. So if we take here alpha as 1 upon sk transpose yk and you choose beta to be minus 1 upon this quantity, then we see that this bkyk will get cancelled with this bkyk and rest out on the left hand side as sk, which is identical with the right hand side. So we note here that the value of alpha is equal to 1 over sk transpose yk and beta is equal to 1 over yk transpose bkyk. The negative of this quantity satisfies this equation. So accumulately alpha is equal to this, beta is equal to this expression, u is equal to sk and v is equal to bk into yk satisfies this equation. And now plugging these expressions of u, v, alpha and beta in this expression of bk plus 1, we will get a possible expression of bk plus 1 that is given by bk plus 1 is equal to bk plus 1 divided by sk transpose yk times the matrix sk transpose minus 1 over yk transpose bk into yk times the matrix bkyk into bkyk transpose. This formula is the first quasi-Newton update for the matrix bk plus 1 that is an approximation of the inverse of the Hessian of the function f at the point xk plus 1. And this quasi-Newton update was derived by Davidon in the year of 1959 and later by Fletcher and Powell in the year of 1963, and hence it is called Davidon, Fletcher and Powell's method, or abbreviately that I have written already over here, that DFP method. Davidon derived in the year of 1959, and later the same formula was found by Fletcher and Powell in the year of 1963, and hence the name DFP method, or these as DFP update for the matrix BK plus 1. Now with this BK plus 1, let us go then computing the direction dk given by minus bk times the gradient gk, and with that direction dk, provided this bk plus 1 is positive definite, we have a descent direction, and with that descent direction we can then find an optimization method, and that optimization method is named as the DFP method or quasi-Newton method with DFP update. Let me neatly write out the algorithm for optimization method to solve an unconstrained optimization problem with this DFP update. To solve an unconstrained optimization problem, minimization of fx, where x is having n many components. Here we assume that this function f is a twice continuously differentiable function. In the algorithm for Quasi-Newton method with DFP update, we start with initializing the process that you provide the objective function, the expression of the objective function, then give the initial iterate x naught, then give the initial matrix b naught to start the process of this DFP update. We notice that in finding the sequence bk, we have to start with one given matrix b naught, right? So that b naught we have to pass over here in the initialization step, which you may consider simply a positive definite symmetric matrix, may possibly be, let's suppose, the identity matrix of order n, or else you also can give any symmetric and positive definite n by n matrix. You also provide epsilon greater than 0, that is as usual the termination scalar to terminate the process, for which norm of the gradient is less than epsilon. This epsilon is also referred as tolerance level, so you pass this tolerance level or the termination scalar and initialize the iteration number or iteration counter to be k is equal to 0. After initializing, we start the main steps. In the main steps, we at the beginning check the norm of the gradient at the current iterate. Check if it is less than epsilon, then you stop and provide xk as one of the stationary points or an optimum point. If however this norm is having value greater than epsilon, then you go for computing the next iterate x1. In computing the next iterate, we have to find the direction of movement dk. In the Quasi-Newton method, it is given by minus bk times gk, which we call as deflected gradient. Then you compute the step length to be taken along the direction dk. This alpha k is argmin of the function f along the direction dk. If you go with the exact step, then you have to compute this argmin, or otherwise you can also choose this alpha k by any of the inexact line search method. Then compute the next iterate xk plus 1, which is given by the current iterate plus alpha k times dk. Then for the next iterate, the matrix bk plus 1 has to be computed over here, for which we will require the vectors sk and yk, where sk is given by xk plus 1 minus xk and yk is given by the gradient at xk plus 1 minus the gradient at xk. Then we compute this bk plus 1 by the DFP update. We may refer here, if we are using the DFP update formula, as the notation bk plus 1 dfp, which is given by this formula that we wrote over here. Maybe we subscript here by dfp. So here we will have bk plus 1 dfp given by this expression, where this bk is with subscripted dfp here, and subscripted dfp here. Now after computing this bk plus 1, again go back in checking the norm of gk is less than epsilon or not. If not, then go again computing all these steps unless and until you find a point xk at which the norm of the gradient is less than epsilon. So unless and until you have norm gk not less than epsilon, you go for computing all these steps, keep computing, and end up when you find a point xk at which the gradient has norm less than epsilon. So this is the first step in the main steps, and the second step is, after this while loop, you give the output as the point xk as a stationary point, which may possibly be an optimum point of the objective function f. So this is the entire algorithm for the DFP method. Immediately after this algorithm, we have quite a few results to be derived for the DFP method. The first and foremost question is that whether the DFP method has the decency property, whether it has quadratic termination property, and whether it has global convergence property. We notice that if the matrix, this BKDFP, is a positive definite matrix, then certainly this dk is a descent direction, and hence the DFP method or DFP algorithm will provide a sequence xk that has the decency property. That is, across the iterates you will have fxk plus 1 lesser than fxk. But what is the certainty that this BKDFP across the iterations will be positive definite? Yes, there is a certainty that if we start with this B naught DFP, a symmetric positive definite matrix, then we can certainly see that this BK plus 1 DFP, this expression is a symmetric matrix, and we can prove that this is a positive definite matrix provided the curvature condition SK transpose YK greater than 0 is satisfied. So we next go for deriving this result, positive definiteness of the matrices Bk plus 1 in the DFP update. The result neatly states that let the matrix B naught, the initial matrix, be positive definite and a symmetric matrix, and suppose the sequence generated by the DFP method is the sequence xk. Then the DFP update bk plus 1 is equal to this expression maintains positive definiteness and also symmetricity provided the curvature condition sk transpose yk greater than 0 is satisfied. This symmetricity of this matrix bk plus 1 is trivial. If bk is symmetric, then you notice that you take transpose of these two expressions, you will get the same expression, and hence bk plus 1 is a symmetric matrix provided the matrix bk is a symmetric matrix. So we will just go for proving the positive definiteness. The proof of the positive definiteness will be done with the help of the mathematical induction. Note that the matrix B naught is given to be a positive definite matrix, and let BK be positive definite. Then we will prove that BK plus 1 is positive definite. That is, we will prove that for any given non-null vector Z, we have Z transpose BKZ greater than 0 for all non-null z. Now to prove that this quantity is greater than 0, we go with the expression of this quantity. We see that this quantity is Z transpose BKZ. Oh, sorry, we have to prove that this Z transpose BK plus 1Z is greater than 0. Because BK is positive definite already assumed. Note that this expression is equal to Z transpose BKZ plus 1 over SK transpose YK. Then look at this expression. If we take Z transpose and then multiply with Z, we will have here Z transpose SK square minus Z transpose BKYK square divided by YK transpose BK times YK. So this is equal to 1 over YK transpose BKYK into Z transpose BKZ, this expression times YK transpose BKYK minus Z transpose BKYK square of it plus the rest out expression 1 over SK transpose YK times Z transpose SK square. Now here this expression can be written, the expression in this bracket can be written in the following manner. Notice that BK is assumed to be positive definite. So with the Cholesky factorization, BK can be written as L transpose, where L is a lower triangular matrix with all the entries in the diagonal positive. And now we take a vector A to be defined by L transpose Z and define the vector B by L transpose YK. Then we notice that this Z transpose BKZ can be written as A transpose A. So we write here A transpose A. This expression YK transpose BK into YK can be written as B transpose B minus this expression is your A transpose B its square, and it is multiplied with 1 over B transpose B plus the rest out expression SK transpose YK times Z transpose SK square of it. Now here, with the help of the Cauchy-Schwarz inequality, we notice that this expression in the bracket is a non-negative quantity. This B transpose B is a positive quantity, and this term is a non-negative quantity. So this entire quantity is non-negative provided this factor in the down SK transpose YK is greater than 0. This is by applying the Cauchy-Schwarz inequality. So we are almost done, that this Z transpose BK plus 1Z is greater than equals to 0. But we have to prove that this is strictly greater than 0 for any non-null vector Z. Now we see that this expression Z transpose BK plus 1Z is equal to 0 if we have this quantity in the bracket is equal to 0 and this quantity Z transpose SK is also 0. So we write here that and Z transpose BK plus 1Z is equal to 0 if and only if you have this quantity is equal to 0, and we all know in Cauchy-Schwarz inequality this quantity is equal to 0 provided the vectors A and B are parallel to each other, and this quantity has also to be equals to 0. So we need to have Z is perpendicular to SK. That is, if and only if you have this L transpose Z is parallel to L transpose YK, and you have z perpendicular to sk. That is, as this L is an invertible matrix, we must have z parallel to yk and z perpendicular to sk. That is, we must have that sk is perpendicular to yk, or you must have z is equals to 0. But we notice that both of these things are not possible because we are going to prove that this quantity is positive only for z not equals to 0. So this z equals to 0 is sorted out, and sk cannot be perpendicular to yk because you have pre-assumed the curvature condition that sk transpose yk is positive. So sk transpose yk cannot be 0. So this is impossible, and hence we have z transpose bk plus 1 z greater than 0 for all non-null vector z in the n-dimensional Euclidean space Rn. And that is precisely you wanted to prove that this bk plus 1 is positive definite. So by the principle of mathematical induction, then this result, the result 1 for the DFT algorithm is true, that provided the curvature condition is satisfied, the sequence bk generated by the DFT algorithm is a sequence of positive definite matrices. Now let me go for checking the quadratic termination property. Or before that, let me mention that the decency property for the DFT algorithm is there. This is due to the positive definiteness of the matrix BK. So as a note, I write here that the DFT method has the decency property because the direction dk for the DFT method, this expression gives us a descent direction for the function f, and hence DFT method has the property that fxk plus 1 is less than fxk for the iterative sequence xk. Now next, let us go for checking the quadratic termination property of the DFT method. We have an affirmative result that the DFT method has quadratic termination property. That is, the DFT method terminates within n iterations for a positive definite quadratic function. So to prove this quadratic termination property, we take the objective function as the expression half of x transpose qx plus b transpose x plus c, which is a quadratic function, and let us suppose the matrix q, which is the Hessian matrix of the function f, is positive definite and it is a symmetric matrix. Then we can prove that if the step length alpha k is chosen with the help of the exact line search, then the sequence say xk generated by the DFT algorithm satisfies the following properties. The first is that the pair yj and sj, they satisfy the quasi-Newton equation with respect to the current matrix bk plus 1 for every j starting from 0, 1, 2 till k. This property is referred as the hereditary property because if yk and sk satisfies this equation, then all the earlier iterates yk minus 1, sk minus 1 or yk minus 2, sk minus 2, or at the end y0 and s0 satisfies this equation. Thus, this equation satisfied by j is equal to 0, 1, 2 till k is referred as the hereditary property of bk plus 1, as if bk plus 1 satisfies all the equations, those are satisfied by its parents and forefathers. The second is that the vectors si and sj for j is equal to 0, 1, 2 till I minus 1, these two vectors are perpendicular to each other with respect to the matrix Q. That is, Si transpose Q Sj is equal to 0 for all j 0, 1, 2 till I minus 1. This equation Si transpose Q Sj is equal to 0 is called the conjugate direction equation, as if this vector Si is perpendicular to Qsj, and hence this equation is called conjugate direction property. And finally, the third point is that the DFT method for this function f with positive definite Hessian terminates within n steps. That is, the method terminates at m plus 1 steps where m plus 1 is less than n. And if your m is equal to n minus 1, then the matrix Bm plus 1 or Bn is equal to exactly the inverse of the Hessian Q. I will not go to prove this result. For a proof of this result, the quadratic termination property, you may please visit the book by Sun and One at the page number 215, where you will find the theorem 5.1.7. It is on the book by Sun and One entitled Optimization Theory and Methods that I have referred many a times in the previous lectures. Now here, looking at the second property, we see that Si and Sj are conjugate to each other with respect to the Hessian matrix Q, and the DFT method moves along the directions xk plus 1 minus xk, that is along the direction sk's, right? So this DFT method moves along the directions S0, S1, then S2 and so on, and these directions are conjugate with respect to the matrix Q, and hence Quasi-Newton method is also called a conjugate direction method. In the next lecture, we will consider in detail the conjugate direction method, where with respect to the Hessian matrix, we will derive conjugate directions, and along those conjugate directions of the Hessian matrix of the given objective function, we will make movements of the optimization method, and hence that method will be called as conjugate direction method. As this DFT method follows conjugate directions with respect to the matrix Q, the Quasi-Newton method is also called a conjugate direction method. So I make a note here. Due to the second property, Quasi-Newton method is a conjugate direction method. You know, this DFT algorithm or DFT method is the seminal Quasi-Newton method, and it has been widely used in many computational softwares and practical problems. It has played an important role in theoretical analysis and numerical computing in the advancement of Quasi-Newton methods. However, it turns out that in case of non-quadratic problems, that means in case of the objective function is not a quadratic function, and with large number of variables, this algorithm, the DFT algorithm, has a tendency of sometimes getting stuck at a particular point and not being able to move further from that particular point. And this stocking phenomenon is attributed to the matrix Bk becoming nearly singular or ill-conditioned. In the next, we discuss an algorithm which is known as BFGS Quasi-Newton method that alleviates this problem of becoming nearly singular for the matrix Bk in the DFT method. The BFGS method was discovered independently by four optimizers, four optimization specialists: Broyden, Fletcher, Goldfau, and Sano. All these four optimization specialists, they have derived a quasi-Newton update formula for computing the Hessian approximation. They have considered not the computation of inverse of Hessian, but they have considered approximating the Hessian and then getting an inversion formula. And all these four optimization specialists, they have derived in the same year 1970. They have independently derived, and thus this method is named after all these four optimization specialists, Broyden, Fletcher, Goldfarb and Sano, and abbreviately we name the method as BFGS method. The idea in the BFGS method in computing an approximation of the inverse of the Hessian is as follows. We notice that the quasi-Newton equation with respect to an inverse Hessian approximation is given by bk plus 1 yk is equal to sk. Then we see that this quasi-Newton equation with respect to an approximation of the Hessian, say an approximation at the point xk plus 1 as ck plus 1, this quasi-Newton equation becomes this bk plus 1 inverse will get on the right hand side. So the quasi-Newton equation with an Hessian approximation ck plus 1 is ck plus 1 sk is equal to yk. Now we consider to find a rank 2 modification formula for ck plus 1. That is, we go for computing ck plus 1 with the help of ck and adding two rank 1 matrices. Those are, say, alpha dash, a constant, a scalar, times u dash transpose plus beta dash times v dash transpose, where these alpha dash, beta dash, they are two scalars, two constants, and u dash, v dash are two vectors in Rn. So we consider to find ck plus 1 in terms of ck by this expression, where this ck plus 1 has to satisfy this equation. Now we recall here the formula for the DFP method. In the DFP method, we had this equation and we had the update formula for bk plus 1, an expression which is exactly similar to this one, where ck is being replaced by bk, alpha dash, u dash, beta dash, v dash being replaced by alpha, u, beta and v, right? So similar to the derivation of the DFP update formula, we can get possible choices of this alpha dash, beta dash, u dash and v dash just by interchanging the role of yk and sk in the DFP update formula. So we get here a similar derivation of the DFP method, and the expression for ck plus 1 is given by ck plus yk transpose divided by yk transpose sk minus ck sk into ck sk transpose divided by sk transpose ck times sk. But at the end of the day, we have to compute bk plus 1, right? An approximation to the inverse of the Hessian at the point xk plus 1. Otherwise, we cannot go for the direction dk given by this bk times gk. If we go for just applying here this dk is equal to minus ck gk, then that does not mimic the Newton's direction, because in the Newton's direction you should have here this matrix inverse of the Hessian at the point xk. So although we have found here a formula for ck plus 1 with the help of ck, but ck plus 1 is an approximation of the Hessian, right? But we need to employ an approximation of the Hessian inverse. So what we do here, we go for computing the inverse of this ck plus 1 and take that inverse of ck plus 1 as your matrix bk plus 1, and then you go with that formula for bk plus 1 or that formula for bk to be employed in finding this descent direction. So here then we have to find an expression of the inverse of this matrix ck plus 1. To find an expression of the inverse of this matrix, we employ here Sherman-Morrison formula, for inversion of a typical matrix, which is as follows, that let capital A be a matrix that is non-singular and U and V are two column vectors. Let us suppose A be a matrix of order n by n and U and V are two vectors in Rn such that 1 plus V transpose A inverse times U is not equal to 0. Then we can show that the matrix A plus UV transpose is non-singular and the inverse of the matrix A plus UV transpose is equal to A inverse minus A inverse U into V transpose A inverse multiplied with 1 over 1 plus V transpose A inverse U. Now we look at this expression. This expression looks like CK plus UV transpose plus another U dash V dash transpose, right? So to compute inverse of this matrix, we apply this Sarman-Morrison formula twice, and you will get that if we write that CK plus 1 inverse as BK plus 1, or let me write it as BK plus 1 subscripted BFGS, then this expression is equal to BK BFGS plus this expression where this BK BFGS is equal to the inverse of the matrix CK. This entire expression may look bit odd. We can write this entire expression maybe in a bit compact manner as the identity matrix of order n minus SKYK transpose divided by the scalar SK transpose YK times BK times IN minus YK SK transpose divided by SK transpose YK plus SK transpose divided by SK transpose YK. And as here in finding this BK plus 1 BFGS, we notice that we have just interchanged the role of YK and SK in the quasi-Newton equation, and then we have found this CK plus 1, and then we have taken the inverse of this CK plus 1 to get this BK plus 1 BFGS, and therefore this BK plus 1 BFGS, this update formula and the BK plus 1 DFP, these two matrices, these two update formulas are called the dual to each other. That means you just go for interchanging the role of YK and SK to get these two update formulas, and thus they are called as dual to each other. Now here, similar to the positive definiteness of this BK plus 1 DFP, we also have the positive definiteness of the BFGS update provided the curvature condition YK transpose SK greater than 0 is satisfied. Similarly, the quadratic termination property with this BK plus 1 BFGS is similar to that of BK plus 1 DFP. That is the result 1 and result 2 that I have written over here. This result 2, the quadratic termination property, is also valid for the BFGS update or BFGS algorithm. In BFGS algorithm, we have just the DFP algorithm where the formula for BK plus 1 is revised by BK plus 1 BFGS. That is, in this algorithm, you please revise this bk plus 1 DFP by bk plus 1 BFGS, you will get an algorithm that is called as Quasi-Newton method with BFGS update. The Quasi-Newton method with BFGS update has this result 1 valid provided Sk transpose Yk is greater than 0, and also this result, the quadratic termination property, is also valid for the BFGS algorithm, and also the BFGS algorithm has descent property. So I write here that the properties of BFGS algorithm are all similar with DFP algorithm. This BFGS algorithm, is found to be more numerically stable than the DFP method. And in practice, it is seen that some weighted convex combination of this DFP update and BFGS update has more elegant numerical behavior than individually both of DFP and BFGS updates. By that I mean, if you consider the update formula for an approximation of the inverse of the Hessian matrix, if I consider Bk plus 1 given by a convex combination of the DFP update formula and the BFGS update formula, then this weighted convex combination of DFP and BFGS update formulae has more elegant numerical behavior than both of DFP and BFGS updates. This weighted convex combination update for an approximation of the inverse of the Hessian is called Broyden class or Broyden family of updates. And here you notice that if I take lambda is equal to 1, then this Broyden updates reduces to the BFGS update. And if I take lambda is equal to 0, then this Broyden update formula reduces to the update formula of DFP. This Broyden class of update formula is also having the decency property, the positive definiteness, and quadratic termination property similar to the DFP method. We now go for giving two numerical examples, and then the global convergence and local convergence rates of the Quasi-Newton method will be discussed. Before that, let me just give you the effect of scaling of the variable for Quasi-Newton updates. In finding effect of the scaling of the variables, the neat problem before us is finding the following. That let us suppose we are given an objective function of several variables, where the generic variable is x has n many components. Now given these variables x, we consider a transformation of the variable by the transformation x hat is equal to some non-singular transformation matrix T times x. So this transforms the variable space x to the variable space x hat. Now in the x hat space, you find the expression of the revised objective function that is given by f hat x hat. So this f of t inverse x hat is the expression of revised objective function in the x hat space. Now with this objective function f hat, you go for computing the sequence of iterates in the x hat space by employing the DFP or BFGS or any of the optimization methods. Then check that if I compute the sequence xk by the corresponding optimization method in the x space, then the question is xk is equal to the inverse of xk hat? If yes, then we say that the optimization method that we have employed over here to compute xk or xk hat is invariant to this transformation. In the earlier lectures, we have seen that the steepest descent method is not invariant to the scaling of the variables, and the Newton method is independent of the scaling of variables. Similarly, in the quasi-Newton method, we also can realize that the quasi-Newton methods are invariant to the scaling of effect. For quasi-Newton methods, that is this DFP method, BFGS method or the Broyden class, are independent of the scaling of variables provided the matrices in the x hat space, that is BK in the x hat space, satisfies the equation that T times Bk in the x space times T transpose. If this is happen to be true, then the quasi-Newton update or quasi-Newton algorithm by which we have computed this Bkx hat or Bkx, that quasi-Newton method is invariant to the scaling of the variables. This equation actually have come from the expression of the Hessian in the x hat space that we all know is given by T inverse transpose the Hessian in the X space into T inverse, and hence the inverse of this matrix is given by T times the Hessian in the X space into T transpose, where this Hessian has to be computed with the inverse. And notice that this BKX hat is an approximation of this inverse of the Hessian at the point xk. And therefore if bkx hat is equal to t times inverse Hessian approximation at the point xk in the x space, that is your bkx times t transpose, if this equation is valid, then the quasi-Newton method by which we have computed this bkx hat is invariant under the transformation x hat is equal to tx. So I write here as a result, quasi-Newton methods are independent of this transformation, which is a particular case of affine transformation. In fact, we can add here a vector, a constant vector say b in Rn, and then we can get this as an affine transformation. With the help of this affine transformation, we can even prove that this equation for Hessian is valid, and therefore quasi-Newton methods are independent of affine scaling of the variables. By affine scaling, I mean you transform the variable by the transformation tx plus b, and you get the x hat space, and in the x hat space now you compute the xk hat, the sequence, by a quasi-Newton method. If this equation is valid, then we can prove that that particular quasi-Newton method is independent of this affine scaling of the variables. Now next I will give one numerical example of DFP algorithm. The problem here is to locate the minimizer or the minimum point of the function fx is equal to half of x transpose times a matrix of order 2 by 2. Here I am considering the function as a function of two variables. So x has two components, say x1 and x2, minus a vector minus 1 1 times the variables x1 x2. We are going to locate a minimizer of this function by DFP method, and in employing the DFP method we take the initial point as the origin of the R2 plane, take the initial matrix B0 DFP as the identity matrix of order 2 by 2, and use the exact line search for computing the step length, and the termination scalar epsilon is to be taken as 0.01 say. Now to compute the DFP iteration sequence xk's, you notice that we need to compute at every iteration the gradient of the function f. For a general point x1, x2, the gradient of the function f is given by this expression. Now let us go for the iteration. In the first iteration, we have the initial counter k is equal to 0. The gradient at the initial point x0 is given by plus 1 minus 1. The direction d naught is given by b naught dfp times g naught, that gives us minus 1 1. Now here, as the function f is quadratic, we can find that the exact step length at the current iterate xk is given by gk transpose dk divided by dk transpose q dk, where q is this matrix of order 2 by 2, the Hessian of the function f. With this formula of alpha k, you can find that the value of alpha naught is equal to 1. And therefore, the next iterative point x1 is given by x naught plus alpha naught d naught, that is equal to minus 1 1. Now we go for computing b1 dfp. For that we require s naught, which is given by s1 minus x naught, that is equal to minus 1 1. We also require y naught, that is g1 minus g naught, which is equal to minus 2 0. And therefore b1 dfp is equal to b naught dfp plus s naught transpose divided by the scalar s naught transpose y naught. This is just a convenient way of writing. This writing is just informing us you compute 1 over s naught transpose y naught, then multiply this scalar with the matrix s naught transpose. Similarly here, the rest expression is negative b naught y naught times b naught y naught transpose divided by y naught transpose b naught y naught, where this b naught is b naught dfp. Here also b naught dfp. You please go for checking that this matrix will be given by half times 1 minus 1 minus 1 3. Verify it. Now at the end of the iteration 1, we check if the gradient at the current iterate x1 is less than epsilon or not. You will find that this quantity is greater than the epsilon value. Epsilon is equal to 0.01. Please verify it, and therefore we proceed to the next iteration, iteration 2. In the next iteration, we have the iteration counter k is equal to 1. We have g1 minus 1 minus 1. Well, I have informed here what is g1. So this norm of g1, you can quickly identify it is given by under root 2, which is greater than epsilon. Here d1 is given by b1 dfp times negative gradient, which is the vector 0 1. So for computing alpha 1 by the formula that I wrote over here, this expression, you will find that alpha 1 is given by half, and hence the next iterative point x2, which is given by x1 plus alpha 1 d1, is equal to minus 1 3 by 2. And at this point x2, you can find that the gradient is equal to 0, which is less than epsilon, and hence we have to terminate the process, and this is a stationary point of the given problem. And as the given problem, the given objective function is a quadratic function with positive definite Hessian, this point at the end of this DFP method, the point minus 1 3 by 2, is a global minimizer of the function f. And here you can verify that the DFP method is getting terminated within two number of steps. The number of variables. The number of variables of the objective function here is equal to 2. Now the result 2 for the DFP method that I have mentioned earlier informs that once a DFP method is applied on a quadratic function with positive definite Hessian matrix, then the DFP method will get terminated within n number of steps where n is the number of variables. Here the number of variables is equal to 2, and we are observing here that within the iteration number 2, the DFP method got terminated. You can also verify that the directions of movements d naught and d1 that we have computed in this particular problem satisfies this equation, and hence d naught d1 they are conjugate to each other. You please verify it, and also verify that if we go for computing b to dfp, that is in the iteration number 2, if we compute the update matrix B to DFP, then you will find that this B to DFP is inverse of the Hessian matrix Q of the objective function. I am keeping this verification also as a home task. These two verifications are aligned with the result 2 that I have mentioned earlier for the DFP method. Now I will give another home task here, that with the help of the BFGS update formula, you solve the following problem, that locate the minimizer by BFGS algorithm for the function f given by half x transpose these 2 by 2 matrix, and x has two components x1 x2. You consider this objective function and then apply the BFGS method to find a local minimizer of this objective function. You take the initial update formula B naught BFGS is the matrix I2, initial point as the origin of R2, step length by exact line search, and the termination scalar as 0.01. I am keeping this as a home task just to verify whether you are aligned to the correct calculation or not. You may check that for the given x naught, the value of the vector x1 is 0 half, the step length alpha naught is equal to half, the direction d naught is this unit direction, and b1 bfgs is the matrix, this matrix, and you will end up with the point x2 as the point 35. You also can verify that if you compute B to BFGS, then you will find that this is the matrix 2335, which is the inverse of the Hessian of the objective function. Now we will go for the convergence property, the global convergence and local convergence rate of the quasi-Newton methods. For the global convergence of quasi-Newton methods, we need to have the following assumptions, that for the global convergence, we consider that the objective function f is twice continuously differentiable on a convex set say capital D, and also assume that the objective function is uniformly convex on the initial level set. That is, on the convex set L naught, that is the collection of points in Rn for which fx is less than equal to fx naught, where x naught is the initial point. By uniform convexity on this set L naught, we mean there exists two positive quantities, small m and capital M, two constants, such that m times norm u square less than equal to u transpose the Hessian into u less than equal to capital M into norm u square for all u belonging to L naught. This assumption, the assumption 2, implies that the Hessian, this matrix, is positive definite, that is, this matrix is positive definite on L naught, and the function f has a unique minimizer, say x bar, in L naught. Under these two assumptions, the assumption 1 and 2, the quasi-Newton methods with exact line search or Wolf-Powell inexact line search converges to x bar globally. That is, neatly, the global convergence result states that suppose the function f satisfies the above two assumptions, then under exact line search or by weak Wolf condition or Wolf-Powell inexact line search, the DFP or the BFGS method converges to x bar from any initial point x naught belonging to Rn. For the proof of this result, you may please visit the theorem number 5.35 on the page 234 and the theorem 5.36 on the page 238 of the Sun and One's book. This theorem 5.35 gives a proof for exact line search, and this theorem 5.36 gives a proof for the inexact line search. Now, after knowing this global convergence result, we will now go for estimating the rate of local convergence of the quasi-Newton methods. In estimating the local convergence rate of quasi-Newton methods, we broadly take the assumption that the Hessian matrix is a Lipschitz function around a local minimizer x bar of the objective function f. We neatly take the following assumptions for the local convergence rate of the quasi-Newton method. For the unconstrained optimization problem to be solved, that minimize the function f, we assume that the function f is twice continuously differentiable on an open convex set, say D. We also take the assumption that the objective function has a local minimizer, say x bar, inside the set D, and at the point x bar, the Hessian matrix is symmetric and positive definite. The third assumption is that there exists a neighborhood of the point x bar, say the neighborhood nx bar epsilon, inside which the Hessian matrix is Lipschitz. That is, this norm is less than some positive constant gamma times norm of y minus x. Now, under these three assumptions, the local convergence of quasi-Newton method states that let the function f satisfies the assumptions 1, 2, and 3. Then consider the iterative sequence given by the iterative formula. Xk plus 1 is equal to xk minus bk inverse times gk. This iterative formula is referred as pure quasi-Newton iterative formula because here the step length is chosen to be 1, like the pure iterative formula for the Newton's method and the pure steepest descent method, where we employ the step length as the constant step 1. For this pure quasi-Newton iterative formula, where this bk is a sequence of positive definite and symmetric matrices, if the generated sequence xk converges to the local minimizer x bar that we have assumed in the assumption 2 here, if the sequence xk converges to x bar, then this convergence xk to x bar is superlinear if and only if the Dennis-Morey characterization of superlinear convergence is satisfied. The Dennis-Morey condition is that limit k tends to infinity, norm of bk minus the Hessian at x bar times the vector sk divided by norm of sk is equal to 0. This condition is called Dennis-Morey characterization or Dennis-Morey condition for the superlinear convergence of a quasi-Newton algorithm. Oh, I am very sorry. I have used in this quasi-Newton iterative equation xk plus 1 equals to this equation. Here I have used bk inverse. Okay, let us go with bk inverse itself. So throughout the lecture, as and when I am using bk inverse in this iterative equation, then by that we shall mean bk is an approximation of the Hessian matrix. But if I am using bk times gk in this iterative equation, then in that case we shall mean bk is an approximation of the inverse Hessian of the given function. Let us now go for proving this result. For the forward part of the proof, let us name this condition as abbreviately say dm. So for the forward part, we suppose that this Dennis-Morey condition holds. Now we will go with a calculation for the numerator in this Dennis-Morey condition. We see that in the numerator of the Dennis-Morey condition we have bk minus Hessian at x bar times the expression of sk, that is xk plus 1 minus xk. Then in the expanded form, it is bk times xk plus 1 minus xk minus the Hessian at x bar times xk plus 1 minus xk, which by the definition of this iterative formula, xk plus 1 is equal to xk minus bk inverse gk, gives us this bk times xk plus 1 minus xk as minus gk minus the Hessian at x bar times xk plus 1 minus xk, which is equal to gk plus 1 minus gk minus the Hessian at x bar times xk plus 1 minus xk minus gk plus 1. And therefore, gk plus 1 can be written as gk plus 1 minus gk minus the Hessian at x bar times xk plus 1 minus xk minus bk minus the Hessian at x bar times sk. We shall require this equation later, and thus let us name it as, let's suppose, the first equation. Now this equation, we notice that implies the norm of gk plus 1 divided by the norm sk is less than equal to norm of gk plus 1 minus gk minus this Hessian at x bar times sk divided by norm of sk plus norm of bk minus the Hessian at x bar times sk divided by the norm of sk. Now we will do a bit analysis for the numerator of this first expression. We see that this gk plus 1 minus gk minus the Hessian at x bar times sk is equal to, by the mean value theorem along the direction of sk to sk plus 1 along this line, you will have this gk plus 1 minus gk Hessian at some point, say xk hat, where xk hat is a point in between this line segment joining xk and xk plus 1 times sk minus this rest out quantity, the Hessian at x bar times sk. And therefore, the norm of this quantity is equal to norm of this quantity, which is less than equal to. As the Hessian is considered to be, here we have assumed that Lipschitzian with the constant gamma inside a neighborhood of the point x bar. So if the sequence xk converges to x bar, then obviously after certain index number, xk lies inside this neighborhood in which the Hessian is Lipschitzian. So after certain index number, say k greater than equals to k naught, we will have this norm less than gamma times the distance between xk hat minus x bar times the vector sk, where this xk hat is a point in between this line segment xk to xk plus 1, and hence xk hat can be written as lambda times xk plus 1 minus lambda times xk plus 1. So finally, by this inequality, we will have here that this left hand side norm of gk plus 1 divided by norm of sk is less than equal to this quantity gamma times norm of, instead of lambda I must have taken here subscripted k, to indicate that this x hat k is for the index number k. So here lambda k, where this lambda k is a number in between 0 and 1. Now here the expression comes out to be this expression plus norm of bk minus the Hessian times sk divided by norm of sk, which further gives less than equal to gamma times lambda k into xk minus x bar plus 1 minus lambda k times xk plus 1 minus x bar plus this expression, which is then less than equal to gamma times norm xk minus x bar, because this lambda k is in between 0 and 1, plus norm of xk plus 1 minus x bar, plus this expression. Now, as we have assumed that the sequence xk converges to x bar, and also we have assumed here for the forward part that this Dennis-More condition satisfied. So we have this xk converges to x bar and this quantity converges to 0 as k tends to infinity. So this right hand side converges to 0 as k tends to infinity. And hence what we have is that limit k tends to infinity of the left hand side norm of gk plus 1 divided by norm of sk is equal to 0. We name this equation as, let's suppose, the equation number 2. We shall require this equation later. Now we notice that in the statement of the theorem we have assumed that the Hessian matrix at x bar is symmetric and positive definite, and also as the function is twice continuously differentiable, this Hessian is a symmetric and it is continuous inside the set capital D in which the function is assumed to be twice continuously differentiable. So this Hessian is symmetric and continuous on the set D that contains the vector x bar. So due to these two conditions, we have a sufficiently small neighborhood, say nx bar, of the point x bar, where this nx bar is inside the set D, in which, that is inside this nx bar, the Hessian is symmetric and positive definite. This is due to the positive definiteness of this matrix at the point x bar and continuity of this Hessian matrix at each and every point inside this nx bar, inside the set capital D. Now, as we have assumed that the sequence xk converges to x bar for the forward part, so there certainly exists some index number, say k naught, such that this sequence xk belongs to this neighborhood after the index number greater than equals to k naught. And hence, what we will have is that the norm of gk plus 1, which can be written as norm of gk plus 1 minus the gradient at x bar, where this is a null vector. So these two quantities are identical. Now by the mean value theorem, you will have this quantity as Hessian at a point x dash, where x dash is lying in the line segment joining xk plus 1 and x bar, and this line segment is inside the neighborhood nx bar. This Hessian at x dash times xk plus 1 minus x bar. This quantity is greater than equals to some beta times norm of xk plus 1 minus x bar, where this beta is a lower bound of the norm of the Hessian on the closure of the neighborhood in x bar. As the closure of this neighborhood in x bar is a closed and bounded set, and the Hessian is positive definite, and the Hessian is continuous inside this set, we certainly have a lower bound of the norm of this Hessian with respect to some matrix norm. And hence this quantity is bigger than equals to some beta times this norm. And therefore, we have from this inequality that norm of gk plus 1 divided by norm of sk is greater than equals to beta times norm of xk plus 1 minus x bar divided by the norm of sk, but we notice that this norm of sk is equal to norm of xk plus 1 minus xk, which is less than equal to norm of xk plus 1 minus x bar plus norm of xk minus x bar. And hence we will have here bigger than equals to this quantity divided by norm of xk plus 1 minus x bar plus norm of xk minus x bar, which can be written as beta times rk divided by 1 plus rk, where this rk is a sequence of real numbers ratio of this norm and this norm for every k starting from 0, 1, 2 and so on. Now we refer to this equation, the equation number 2. We have this ratio norm of gk plus 1 divided by norm of sk tends to 0, and hence here we will have rk divided by 1 plus rk tends to 0 as k tends to infinity. So we have here the sequence rk divided by 1 plus rk is greater than equals to 0 by the definition of rk. As well, this is less than half as this quantity is tending to 0. Maybe this is less than half after certain index number, say k greater than equals to k dash. So we have here that 0 less than equal to rk less than 1. You multiply on both the sides by this 2 times rk and then less than equal to 1 plus rk. You will get rk less than 1. So maybe this is after k greater than equals to k dash, and therefore we have 1 less than equal to 1 plus rk less than 2 for all k greater than equals to k dash. So 1 by rk plus 1 is greater than half. So from this inequality, maybe let us name it as 3. We have rk less than equal to 2 by beta times norm of gk plus 1 divided by norm of sk, which tends to 0 as k tends to infinity, and therefore the sequence rk tends to 0 as k tends to infinity, and that gives limit k tends to infinity of xk plus 1 minus x bar its norm divided by xk minus x bar is equal to 0, and hence the sequence xk converges to x bar superlinearly. Now next we will prove the reverse part of the result, that we assume that this sequence xk converges to x bar superlinearly, And then we have to prove the Dennis-More condition. For the converse part, suppose the sequence xk converges to x bar superlinearly, and the point x bar being a minimizer, we have the gradient at x bar is equal to 0. Now we see that the norm of gk plus 1 is equal to the norm of gk plus 1 minus g at x bar, because g at x bar is equal to 0, which is by the mean value theorem less than equal to the Hessian at some point x double dash, where x double dash lies in between the line segment joining x bar and xk plus 1. This norm times xk plus 1 minus x bar its norm, which is less than equal to some positive constant beta bar times xk plus 1 minus x bar. This is less than equal to beta bar because, or let me keep it as home task. Let you be bit attentive and now find why this can be written as this norm is less than equal to beta bar. Try to find it out so that you will become attentive. We'll require this inequation later. We name it as say 4. Now as the sequence xk converges to x bar superlinearly, we can prove that we will certainly have limit k tends to infinity norm of xk plus 1 minus xk divided by norm of xk minus x bar is equal to 1. This is very trivial to prove. You can just quickly go with one inequality that this is indeed true, because you see that this ratio norm of xk plus 1 minus xk divided by norm of xk minus x bar is equal to norm of xk plus 1 minus xk plus x bar. Sorry, here we must have here x bar. In the numerator, we will have norm of xk minus x bar. This is greater than or equals to modulus of norm of xk plus 1 minus x bar divided by norm of xk minus x bar minus norm of xk minus x bar divided by norm of xk minus x bar. And as this left hand side, this portion tends to 0 as k tends to infinity, we will then have the limit of this ratio, that is this ratio is equal to 1. Now with the help of this limit from 4, we see that we have 0 is equal to limit k tends to infinity norm of xk plus 1 minus x bar divided by norm of xk minus x bar is greater than equals to limit k tends to infinity norm of gk plus 1 divided by beta bar times norm of xk minus x bar, which can now be written as limit k tends to infinity norm of gk plus 1 divided by beta bar times xk plus 1 minus x bar into norm of xk plus 1 minus x bar divided by norm of xk minus x. As this limit is equal to 1, I mean limit of this expression, therefore we have here is that limit k tends to infinity norm of gk plus 1 divided by, sorry, I have here, this is not x bar but xk, right? We have xk here, there also xk, and hence norm of gk plus 1 divided by norm of sk is equal to 0. Now we go back to the equation number that we have derived earlier over here, the equation 1. From this equation 1, we bring this portion on the left and take this gk plus 1 on the right and then divide by norm of sk. Then you take the norm. You will get that the norm of this quantity divided by norm of sk is less than equal to norm of this quantity divided by norm of sk plus norm of this gk plus 1 divided by norm of sk. So from this 1 we have that norm of bk minus the Hessian at x bar times sk divided by the norm of sk is less than equal to the norm of this expression divided by the norm of sk plus norm of gk plus 1 divided by norm of sk, which by the mean value theorem can be written as this gk plus 1 minus gk, the Hessian at some xk double dash c, where xk is a point in between the line segment joining xk and xk plus 1. This times sk minus the Hessian at x bar times sk divided by norm of sk plus norm of gk plus 1 divided by norm of sk. Now this quantity, by the assumption that the Hessian matrix is Lipschitzian, we have some gamma times norm of sk square divided by norm of sk plus norm of gk plus 1 divided by norm of sk, which tends to 0 as k tends to infinity, because we have proved here that this quantity tends to 0 as k tends to infinity, and therefore we have here this tends to 0 as k tends to infinity, and hence the limit of this expression is equal to 0 as k tends to infinity, and that is precisely the Denish-More condition. With this I end up this lecture here, and so far in any of the optimization methods that we have described for solving unconstant optimization problems, that is the method of steepest descent, the Newton's method, the quasi-Newton methods, we notice that we have been using the gradient information and the Hessian information or approximation of the Hessian inverse. That is, in computing the directions of movements in the steepest descent or in the Newton method or in the quasi-Newton method, we have been using the information of the gradient, the information of the Hessian, or the information of Hessian inverse, or some approximation of the Hessian inverse. But in the next lecture, we will have a method that is completely out of the box, that to calculate the inverse of the Hessian, we shall use some conjugate directions with respect to the Hessian. At a given point xk, we will consider to find in many directions, say d0, d1, d2 till dn minus 1, or let me subscript by certain k to indicate that these directions are at the current iterate xk. So at the current iterate, we shall consider to identify these n many directions that are conjugate with respect to the Hessian matrix. Then we shall move along these directions to take the next iterative point. And that is precisely the conjugate direction method. The conjugate direction method will be the agenda for the next lecture. And here I must mention that for more detailed convergence result of the quasi-Newton method, you may please look at the chapter 5 of the Sun and One's book, and a nice classical reference for quasi-Newton methods, motivation and the theory. You please look at the article by Dennis and Mori entitled Quasi-Newton Methods, Motivation and Theory, which came out through Siam Review in the year of 1977. This is a classic detailed reference for quasi-Newton methods, their motivation and the theory for the quasi-Newton methods. With the mention of these two references, I end up the lecture here. In the next lecture, the topic of discussion is the conjugate direction method for solving unconstrained optimization problems. Thank you. Thank you all for all of your kind attention.